Welcome everyone to our week 4 recap video. In this video we're covering 3.1 through 3.5 and I've got a few problems selected here for us based on your responses from the participation survey. So the first one here is a mean value theorem problem, but this one actually uses a graph rather than any particular equation for a function. The second one is kind of a bit more of a standard one. For the mean value theorem, well actually this is an application of Rolle's theorem because this average rate of change will end up being 0, and so we'll go over that. Example number 3, I saw some people very interested in how to solve for inflection points, and so I thought I'd do this one. I saw a few questions on this on the Piazza forums and everything. So we want a inflection point at a very particular value of x on this curve, and so we'll show how to do that. Example 4. Horizontal and slant asymptotes, and then example 5 is going to be our curve sketching problem. So these are the problems that I'm going to be doing. Again, feel free to jump around and watch the parts that really interest you. Without further ado, let's do example number 1. All right, so in this example, again, we just have a graph. We don't have actually what the equation is, but we want to go ahead and use this graph to estimate C values that satisfy the mean value theorem. So, okay. First of all, the mean value theorem is one of these theorems that has a list of hypotheses, right? It doesn't work for every single function out there. And so the first thing, especially if this was to show up as a standard response style question, you would definitely have to, justify the hypotheses. And the web work homework got you into that habit as well. The fact that it needs to be continuous on this interval from 2 to 8, and it needs to be differentiable on the open interval from 2 to 8. So when I look at this, right, it's definitely continuous. I could draw this graph here without lifting up my pencil. And it looks to be differentiable as well, right? Because back in chapter 2, we went ahead and we classified all the ways that it wouldn't be differentiable. So, I mean, first of all, if it wasn't continuous, that would be a problem. Or if it had a vertical tangent line, that would be a problem. Or if it had one of those cusps, or kind of the more intuitive way to say that is one of these jagged edges. So because it doesn't have really anything like this, it looks like it's continuous and differentiable, and so we can actually apply the mean value theorem to it. So now let's go ahead and talk about finding C values that satisfy the mean value theorem. So again, the mean value theorem says that there's some place where the slope of the tangent line, so slope of the tangent line, that's going to be the derivative. And again, someplace, I don't know exactly where it is, so I'm going to go ahead and say this is C, so f prime of C, that this is equal to the slope of the secant line. So that's going to be my f of b minus f of a minus b, over b minus a on any particular interval here. And so in this case, we have the interval from 2 to 8. So the interval from 2 to 8, and then the other thing is that we don't really have an f. We want to apply this to g. So really, in our particular case, this says that there's some place where the slope of the tangent line for our function g is equal to the slope of the secant line on our interval from 2 to 8. So I'm going to go ahead and do g of 8 minus g of 2 divided by 8 minus 2. So this is kind of more the algebraic side of things. Now, if I had a very particular equation, right, I could go ahead and calculate out the slope of the secant line, and I could also take the derivative and plug in c, and then try to figure out that slope of the tangent line, right? What value of c does this equal the slope of the secant line? But in this case, because we don't have a function, an equation for our function, we just have the graph. Let's try to look at this from more the graphical viewpoint. So first of all, let's try to find these points, right? So I'm interested in at 2 and at 8. So I'm going to go over here. So at 2, we're talking about this point right here. And at 8, we're talking about this point right here. And so let me go ahead and draw the secant line between these 2 points. And I'm going to do my best to draw a relatively straight line, but it may be off. So something like this. So there is my secant line. And again, what the mean value theorem says is that there's some place where the slope of the tangent line is the same as the slope of the secant line. So, right, and kind of slope is again kind of this rise over run sort of deal. And so, but we can here visualize what the slope of the secant line is. And if we want two slopes to be the same, that means we want them to be parallel, right? So I can go across here And for instance, I think right here, there's going to be a point where the slope of the tangent line is going to be the same as the slope of the secant line because those two lines are parallel. So I'm going to go ahead and guess, right? This is just an estimate. So I'm going to estimate that one possible C value would be 2.5. Based on my graph right here, 2.5 seems to be a reasonable guess. Now there are others. I invite you to pause the video and try to find at least one more C value. So yeah, pause the video and then we'll come right back. All right, so with that, I hope you found somewhere over here, just maybe a little bit beyond 6, maybe it's even equal to 6, but there's some place right over here where the slope of the tangent line would be the same as the slope of the secant line. So again, at C equals, I'm just going to say 6.1 or so, and maybe that's a bit off. Maybe it's supposed to be right there at 6. But this is a place where, again, these two lines are parallel. If I was to draw this tangent line a little bit farther here, hopefully we can see that these are two parallel lines. And that's it. There are extra conditions on the C values. So for instance, right, they have to lie inside of this interval from 2 to 8. But notice that 2.5 and 6.1, they both lie inside of this interval from 2 to 8. And so these are the only two solutions there. All right, that was example number 1. Let's go ahead and move on to example number 2. Example number 2 here is a bit more straightforward as far as we have an equation. Again, we want to go out and find C values, and in this case, they should satisfy the conclusion of Rolle's theorem. So Rolle's theorem, remember, is just a very special case of the mean value theorem. And you could say, well, why even bring up Rolle's theorem? I mean, if the mean value theorem kind of trumps it, right? It covers the Rolle's theorem. Why do we need Rolle's theorem? And the answer is actually, well, the way that you prove the mean value theorem is by first proving a special case of it, Rolle's theorem, and then you can go ahead and prove the mean value theorem. So it's kind of a stepping stone, and that's why it's stuck around, is because really the heart of the mean value theorem, its proof really comes from Rolle's theorem. So the extra condition about Rolle's theorem here is that the function's value at the endpoints are actually the exact same, right? So the function's value at the endpoints are actually the exact same, and we will see that come up in this particular problem. But I'm going to pretend like I forgot what Rolle's theorem even is, right? If you just remember the mean values theorem, then that's all you need. So I'm going to use the mean value theorem on this particular problem. And again, the mean value theorem says that there's some place where the slope of the tangent line is equal to the slope of the secant line. F of b minus f of a divided by b minus a. Okay, so in this case, we have a particular interval of -6 to 1. So again, we're looking for C values here. And let's go ahead, and this is going to be f of 1 minus f of -6 divided by 1 minus -6. So I guess that's going to be 1 plus 6. Okay. Let's go ahead. On the left-hand side, we could take the derivative here. So let's go back up to our equation and take the derivative. So this is going to be 2x plus 5. So that would be our derivative f prime of x. But actually, this says f prime of c. So I guess instead of x here, we should probably be using c's. So, okay, let's go ahead and use a c there. On our right-hand side, let's see, I know that we're dividing by 7. F of 1. So I need to go back to my function's value, my function up here, and plug in 1. So if I do that, let's see, I'm going to get 1 plus 5 minus 6. So that's going to be 6 minus 6, that's 0. And we just subtract away f of -6. So if I go ahead and I plug in -6, well, -6 squared is going to be positive 36. Let's see, -6 times 5 is going to be -30. And then minus 6. So 36 minus 30 minus 6. So that's going to be 0. And you can see, again, Rolle's theorem requires that these two values are actually the exact same. In this case, they happen to both be 0, but they could both be 5, they could both be 4, they could both be, negative 100 pi, right? So, I mean, it could be any of these things. And so long as they're the exact same, Rolle's theorem applies, because when you go ahead and write 0 minus 0, you get 0 divided by 7, and therefore you get 0. So really the conclusion for Rolle's theorem says that f prime of c should be equal to 0. So that's where the 0 comes from, is because these two values are the exact same. So, okay, that's the setup for Rolle's theorem. Again, we should probably make sure, right, that this function here is continuous and differentiable. So looking at this function here, maybe I'm going to go ahead and even write it down. So f is a polynomial. So it is continuous and differentiable everywhere. And in particular, we're interested, right, on this interval from -6 to 1. But again, kind of, it's continuous and differentiable actually everywhere. So any interval that you chose, it would actually work for. So, okay, we have that it's continuous and differentiable. We have now our setup. Again, our setup says 2c plus 5 should equal 0. What c value makes this true? Well, let's go ahead and rearrange here, and I'm going to get 2c is equal to -5. So therefore, c is equal to -5/2, or that's going to be the same thing as -2.5. So c equals -2.5. Double check that this is inside of our interval here from -6 to 1, and it absolutely is. So this right here is going to be my final result. This is the c values. There only turns out to be 1 in this case, but this is the c value that satisfies the conclusion for Rolle's theorem. All right, 2 examples down. Let's move on to example number 3. And in this example here, we want to figure out, some values, unknown constants here, a and b, so that this curve has a point of inflection at a very specific value, right? X equals 1, and it turns out the y value there should be 3. So I guess first of all, the point of inflection, one big thing about inflection points, and maybe let me go ahead and just remind us and draw one of these things. So if I have some curve, a point of inflection is where it changes concavity. So there's kind of 2 big things about this. First of all, a point of inflection is actually a point on the curve itself. It's not just some point, hanging out up here. That's never going to be an inflection point. So it's actually got to be on the curve. And then the other thing is that, this is where concavity changes. And the big way that, you can have concavity change is if your second derivative is either 0 or undefined. So we're going to be looking for, can we get the second derivative equal to 0, or can we get the second derivative undefined? So these are what we're going to be looking for. Okay, so to the first point here, that this actually needs to be on the curve. Well, here's a curve that has different x and y values, and this says if you plug in 1, the y value at that point for x equals 1 should be 3. So that gives us our first piece of information. That, let's see, instead of y, I'm going to write 3 is equal to a times, 1 to the 1/5 power. Well, 1 to any power is just 1, so this is going to be a times 1, plus b times 1 to the -1/5 power. But again, I'm plugging in 1 everywhere I see an x, and so 1 to any power is just 1. And so again, our first piece of information is that 3 should be equal to a plus b. All right, so that takes care of the fact that this point needs to actually be on the curve itself, right? 1, 3 has to satisfy, the equation of this curve. So that tells us a little bit of information about a and b. So we have 1 equation down. I'm probably looking for 1 more equation, right? Because we have 2 unknowns. I probably want 2 equations to be able to solve these things. So, all right, let's go ahead and use the other piece of information here that the second derivative here needs to be either 0 or undefined. So let's go ahead and start taking derivatives. So if I take a first derivative here, well, let's see, that a is constant, so it's just along for the ride. And then when I take the derivative of x to the 1/5, well, using the power rule, the 1/5 comes down, and I reduce my power by 1. So 1/5 minus 1 will be -4/5. Likewise, for the second term here, b is constant, so it's just along for the ride. And then that -1/5 comes down. We use parentheses so that we don't get confused and think this is subtraction or anything like this. And let's go ahead and reduce our power by 1. So -1/5 minus 1, that's going to be -6/5. All right, well, that was 1 derivative. We need to do 1 more derivative, right? Because our information about inflection points is all about a second derivative. So let's go ahead here and do 1 more derivative. And all right, well, let me see here. If I if I take another derivative, again, a is along for the ride. 1/5 is constant. It's along for ride. And let's see, power rule now, right? So if I bring down -4/5 here, again, let me maybe use some parentheses so we see this is all multiplied together. And then I reduce my power by 1. So -4/5, and if I subtract away 1, that's going to be -9/5. All right, and next up, let's go ahead and take the derivative here. So again, b is along for the ride. -1/5, this is a constant, it's along for the ride. And let's see, take the derivative, so my -6/5 comes down, and I reduce my power by 1, so this comes to -11/5. All right, so we can kind of clean this up a little bit. So let's go ahead and clean this up. Oh, we have to multiply a bunch of fractions together. Well, I guess a is not really a fraction, but we can make it into 1 by just doing a over 1. And likewise, we could put this as b over 1. And so when we multiply fractions, right, we just do across the top with the numerators and across the bottom with the denominators. So I have a times 1 times -4, so that's going to be -4a. And in the denominator, 1 times 5 times 5 is going to be 25. And we still have this x to the -9/5 here. For our next one, we have b times -1 times -6. So, okay, I guess 2 negatives, that's going to make a positive 6b. And then 1 times 5 is going to be 25, x to the -11/5. Now, next up, right, we want to have our inflection point when x is equal to 1. So when x is equal to 1, so I need to go ahead and plug in x equals 1 into all of these things. And so I'm going to get -4a over 25, and 1 to any power is just 1, so that's quite nice. So this is going to be multiplied by 1, and of course multiplying by 1 doesn't alter the value at all. So I'm going to do plus 6b over 25, and again, I need to plug in 1 for x. So 1 for x, and well, 1 raised to any power is just 1, and so, okay, that just becomes 1, and 1 times anything is itself. So, okay. So now remember, over here, we need either the second derivative to be equal to 0, or the second derivative to be undefined. Now, unfortunately, there's going to be no way to make this undefined, right, because we don't have any x values or anything like this. We already plugged in 1 for our x value because that's where we want our inflection point to be. And so, right, kind of being undefined isn't really an option here. There's no way to make this undefined. And so our only hope, right, for an inflection point is actually when the second derivative is equal to 0 here. So that's going to be our second equation. Let's go ahead and simplify this down a little bit. First thing, I don't really like fractions so much, so I'm going to go ahead and multiply through by 25. And of course, I need to do this on both sides of my equation. And so I get 0 is equal to -4a plus 6b. And then maybe I could rearrange a little bit and say 4a is equal to 6b. And I'll divide by 2 on both sides. I see there's a common factor here. So this is going to be 2a is equal to 3b. So now I have two equations up here. A plus b is equal to 3. And 2a's should be equal to 3b's. So again, two equations, two unknowns. From here, I'm going to go ahead and try to solve what is a and what is b. My favorite way to solve a system of equations has got to be substitution, whenever it works out fairly reasonably. So I'm going to go ahead and try to use substitution here. So I'm going to go ahead and solve this one maybe for a. So I'm going to write this as a is equal to 3 minus b. And now I can go ahead and substitute. Everywhere I see an a, I'm going to put 3 minus b. So down here, instead of a, I'm going to go ahead and put 3 minus b. And now I can solve this equation for b. So I'm going to have 6 minus 2b's should be equal to 3b's. So 6 is equal to 5b's, and therefore b should be equal to 6/5. So not a very beautiful answer, right? It's a fraction and everything, but this is the value for b. Now, if I want to know what is my value for a, right, we have an equation back here that says, well, if you want the value for a, take 3 and subtract away b, and that will give you your value for a. So I need to do 3 minus b here in order to get a. So down here, I'm going to say a equals 3 minus b. So I found my b value to be 6/5. And in fact, let's go ahead and write this. Instead of 3, let me turn this into 15/5. That's the same thing as 3, but with a common denominator. And so now I can go ahead and simplify this fairly easily, and this is going to be 9/5. So 15 minus 6 would be 9/5. All right. So that would be my correct values for A and B. So again, kind of the big thing, where our two equations came from is, first of all, that the inflection point needs to be a point on the curve. And that told us this information here that 3 should be equal to A plus B. And then the second big piece of information that we needed to use was that in order to have an inflection point, you either need the second derivative to be either undefined or 0. And kind of undefined was out of the question here, right, because we had to plug in 1 for x. So our only hope was that the second derivative was equal to 0. So those two pieces of information combined allowed us to solve for A and B. All right, that is it for example number 3. Let's go ahead and move on to example 4. All right, well, in this problem, example 4, we want to determine if the following functions have any slant or horizontal asymptotes. So the claim is you can only have one or the other, a slant or a horizontal asymptote. Both of these are explorations of what's happening as x goes to infinity or negative infinity. And I should maybe clarify this in case if any, math professors or something watch this. So this is a correct statement if you have rational functions. So because we have nice rational functions here, polynomials over polynomials, it's true you can only have either a slant or a horizontal asymptote. Of course, there are more horrible functions out there, and then you can have, kind of a slant asymptote as you go off to one direction and a horizontal asymptote as you go off to the other direction. But for these relatively nice ones, and for, pretty much all of the problems that we're going to see in our class here, you're going to only have one or the other. And so, okay, the first thing is, right, remember the videos for 3.4, when we were talking about horizontal and slant asymptotes, we had all of these rules, there was this algebraic way to show if you have a slant or a horizontal asymptote. And this is a good way to kind of have you start thinking about how are you going to attack this problem, right? What steps are you going to take in order to solve this? And so it all came down to the degrees of your polynomials on top and bottom. And so looking at this one right here, if you're going too fast, you say, okay, well, I have a degree 2 on top. It's a quadratic, right, because I have an x squared. But then I only have degree 1 on bottom, right, because it's x minus 2 and 3 minus 2x, right? And this is where you have to be careful, because actually your polynomial on bottom is a degree 2 as well. It's just that it needs to be FOILed out, right? You actually need to expand it out, and then you're going to have a degree 2 divided by a degree 2. So let's go ahead and maybe first go and rewrite this. So the top is fine, x squared minus 5x minus 9. And then in the denominator here, let's go ahead and expand this out. So foiling it, we have firsts, so that's going to be 3x. Inners, that's going to be negative 6. Outers, that's going to be negative 2x squared. And last, so negative 2 times negative 2x is going to be positive 4x. And so we can go ahead and simplify this down. Maybe one more line here. Again, the top is staying the same. And we have negative 2x squared plus 7x minus 6. So now we really see that this is a degree 2 divided by a degree 2, and so therefore we are going to have a horizontal asymptote. And the algebraic way of doing this is just looking at these leading coefficients here. So the leading coefficient for the numerator is 1, the leading coefficient for the denominator is negative 2, and therefore we're going to have a horizontal asymptote. So again, this is for part A, has a horizontal asymptote at y equals negative 1/2. So again, you're just taking those leading coefficients, the 1 and the negative 2, and you're using those to come up with your horizontal asymptote. So remember, this works whenever the degrees are equal. But yeah, there were other rules as well, and so I invite you to go back and double check these things. Now, this is fine, right? If this was a multiple choice question, this is a fine way to show your work, or any question that doesn't require, calculus work. But if it requires calculus work, right, if we got one of these as a standard response question, this doesn't really show us any calculus knowledge. Right, and so if I want to showcase my calculus knowledge, after all, we're in calculus class, I would need to go ahead and use one of these limits. So more formally, horizontal asymptotes are an exploration of what's happening when x is going to infinity or negative infinity. And we're going to start off maybe with just infinity here. And we were able to simplify down our function to x squared minus 5x minus 9 divided by negative 2x squared plus 7x minus 6. And remember, the way that you solve these is that you take the, you find the power of the denominator here. In this case, x squared is the largest power of this polynomial here. And we go ahead and we divide by that largest value. So I'm going to go ahead and divide by x squared. Now, of course, if I do that in the denominator, I need to also do that in the numerator, so that way I don't fundamentally change anything. So this is now just a fancy multiplication by 1. Right, so this 1 over x squared divided by 1 over x squared, this is just 1, but it's rewriting 1 in a really fancy way. So now let's go ahead and distribute this to each piece. So in the numerator and in the denominator, we're going to go ahead and distribute this. And so this is going to be equal to the limit as x goes to infinity of, and let's say 1 over x squared times x squared, well, that's just going to be 1. Minus 5, and we have x divided by x squared. So there's one more x on the bottom than there is on the top here. So that's going to be 5 times 1 over x, right? One more on the bottom. And then minus 9, and again, times 1 over x squared. That one doesn't have any x's, so nothing cancels out. And so that's what our numerator looks like. In our denominator here, we have a very similar storyline. For the first one here, both of our x squareds cancel out on top and on bottom. For the second one here, we have plus 7, and 1x cancels out, but there's still one more left in the bottom. And then for our third one here, there's no x's, none cancel out. And so now we can go ahead and use this limit as x goes to infinity. So as x goes to infinity, right, you have 1 divided by something extremely large. So 1 divided by something extremely large, 1 divided by a million, a billion, something like this, right? These are all going to be 0. So I'm just going to go ahead and write this bit here is going to 0. This bit here is going to 0, right? 1 divided by, a million squared, a billion squared, right? Again, very, very large in the denominator. And so all of these things here are going to 0. And so our final result, as x goes to infinity, we get 1 minus 0 minus 0. And again, technically this is like negative 5 times 0, but that's just 0. And same thing here, 9 times 0, but that's just 0. In our denominator, we have negative 2 plus 0 minus 0. So after all is said and done, right, we see that this limit here, as x gets very, very large, again, this is an idea about horizontal asymptotes. As you go kind of to the ends, this is sometimes called end behavior of a function, right? As you go to the very tail ends, right, this is getting closer and closer to negative 1/2. Now, I dealt with when x is going to positive infinity, right? We could have also done when x is going to negative infinity. And the claim is, right, when you take 1 and you divide it by a really, really large but negative number, right? 1 divided by negative a million or negative a billion or anything like this, this also goes to 0. And that was thanks to that nice theorem that we got in the video notes. So kind of whether it's going to positive infinity or negative infinity, these are both approaching negative 1/2. And so yes, we have a horizontal asymptote at negative 1/2, just as we predicted up here using a bit of algebra stuff. And as I said, right, that you're only going to have either a horizontal or a slant asymptote. And because this has a horizontal asymptote, right, we don't have to talk about the slant asymptote at all. I'll go ahead and specify. So this function has no slant asymptotes. Because it has a horizontal asymptote. All right, so let's go ahead and move on to part B. Part B, I made this look very similar to part A, right? You really have to slow down, read the question carefully, and then you'll notice, right, that there's a few changes here, right? Instead of x squared, I have x cubed, and let's see, instead of 5x, I have 5x squared. So I've changed a few values here. Otherwise, the function seems pretty similar. And so likewise, to part A, that maybe the first good step is to go ahead and expand out that denominator. And so if I go ahead and I do this, expanding out the denominator in the same way that I did, again, the numerator staying the exact same, x cubed plus 5x squared. Oh, and I guess, sorry, I see that I made a mistake now. I don't know, at one point, I decided, plus 5x was going to be minus 5x. And man, I just really stuck with that the entire time, right? So, I mean, this should technically be plus. This should technically be plus. And you can see that actually it doesn't really make a difference. It's all coming down to this leading coefficient here, this x squared. And so even though this is plus, now this is really plus 0 right here. And so it doesn't actually change our results. So, okay, but it's good to be correct here. So I'm going to go ahead and make sure that I include the plus. So, okay. That's our numerator, and in our denominator, we went ahead and simplified that one already before. So this is going to be negative 2x squared plus 7x minus 6. And now we can see that, right, we have a degree 3 polynomial on top and a degree 2 polynomial on bottom. And so according to our theorem that we had, right, that there are going to be no horizontal asymptotes. So because the degree of the numerator is larger than the degree of the denominator, there are no horizontal asymptotes. So now we've dealt with the cases, right, when the degree of the numerator and the denominator are the exact same. And we've dealt with the case where you have the degree of the numerator is larger than the degree of the denominator. And you should make sure to maybe pause the video and go back and double check the notes, right? What happens if the degree of the denominator is the big one, right? What happens then? Do we have horizontal asymptotes? Do we not? Where are they? Sort of deal. So make sure that you remember this, especially as you're doing the quizzes, exams, things like that. All right. So now we need to figure out about slant asymptotes. And remember, slant asymptotes come down to this polynomial long division. And so that was another thing that a few students brought up, wanted to see some more polynomial long division. And so I wanted to showcase that here, polynomial long division with this one. So let's go ahead and set this up. So I need to take x cubed plus 5x squared. And a good hint is to use this as a placeholder. So even though there aren't any x terms, I'm going to do plus 0x and then minus 9. And remember, I need to divide this by my negative 2x squared plus 7x minus 6. So I need to figure out, again, I'm trying to divide these two things. And so just like regular long division with integers, right, same sort of storyline here, I need to figure out what should I multiply by negative 2x squared in order to get x cubed. And so let's see, I definitely need an x. So let me go ahead, I need an x. But then somehow, right, this only has a 1 in front of it. This has a negative 2. So somehow I need to get rid of that negative 2 and make it a 1. So let's try negative 1/2 x, right? So if I go ahead and I multiply this by this, right, the negative 2 and the negative 1/2, they perfectly cancel out and you just get 1. And then you get x squared times x, so that's going to be x cubed. So that seems to be working out as I hoped. And remember, you have to go ahead and multiply this across everything. So we have negative 1/2 x times 7x. So that's going to be, minus here, minus 7/2 x squared. X times x, good. And then we need negative 1/2 x times negative 6. So again, negative, negative, so that's going to be plus. In negative 6 times 1/2, that's going to be 3. And looks like there's 1x. So now we need to go ahead and subtract all this away. And right, if you're doing things correctly, this leading term should cancel out. So x cubed minus x cubed, so that becomes 0. So that's great. Here we have 5x squared minus a negative. So right, this is really plus 7/2 x squared. All right, so okay, now we need to start dealing with all these fractions and whatnot. Let me go ahead and just write this to maybe save us that we don't need to deal with fractions so much. 7/2 is the same thing as 3.5. So let's go ahead, minus a negative, so that's going to be plus 3.5 onto 5. So that's going to be 8.5 altogether here, x squared. And then 0x minus 3x. So that's going to be negative 3x. And then we bring down this negative 9. All right, so now we're at the final bit here. We need to ask ourselves, what do we multiply by negative 2x squared in order to get 8.5x squared. Yeah, just like before, this is a bit of a guessing game, right? So you kind of go back and forth a little bit. We see that x squared and x squared, these are already the same, so I don't need any powers of x added to this. And let's see, I'd like to get out 8.5. So let's go ahead. If I just tried, 8.5 times this negative 2x squared, well, that negative 2 is really throwing things off, right? So that's not going to be 8.5, but we're going to have to include that negative 2 bit. And so I'd like that negative 2 maybe to go away here. So I'm going to go ahead and divide by negative 2. So 8.5 divided by negative 2. Now double check. If I take this here and I multiply it by negative 2x squared, again, that negative 2's are canceling out, and then we get x squared, x squared, that's great. So yeah, that works out. So this would successfully be 8.5 x squared. And again, we need to kind of do the rest of this here. But remember, the final answer for what is the slant asymptote is really just the quotient, right? Whatever's up here. So now that I've figured this out, we're essentially done. I mean, you could certainly go ahead and figure out the rest of this just so you have all of your I's dotted and T's crossed. But this right here is going to be the final answer. So the final answer will be y equals negative 1/2 x, and then I'm going to go ahead and write minus. And let's see, if I divide 8 by 2, that's going to be 4. And if I divide 0.5 by 2, it's going to be 0.25. Right, so this right here, negative 1/2 x minus 4.25 is the slant asymptote. Again, we were able to include no horizontal asymptotes for this one, and there is a slant asymptote, and there it is. So if you actually wanted to prove this, then yeah, you'd have to actually do the rest of this and figure out the remainder and take the limit and all that sort of stuff. But if you just ask what is the slant asymptote, right, this is the way that you can go about it. All right, that is it for example number 4. Again, that was kind of a two-parter there, but I wanted to kind of hit both aspects, the horizontal and the slant asymptotes. Let's go ahead and move on to our last question, example 5 about curve sketching. Now, curve sketching is very important. In fact, if you were to probably poll, math instructors or calculus instructors across the nation and ask, what are the core ideas of calculus, right? What do you really need to make sure that students walk away with from your calculus class? And probably there's 3 big topics that everyone would mention, right? So there's the related rates. So this came up in our midterm exam. This was 2.8. So kind of how to relate derivatives together. And you kind of had these real world-ish problems, definitely word problems and whatnot. The second topic, optimization. So that's going to be 3.7. That's going to be next week's stuff. 3.7, optimization. How do you minimize or maximize things? Very important real world skill to have. And then the third one would certainly be curve sketching, right? How does the derivative or second derivative influence the shape or of the curve of a function? And so, again, this is one of the big ideas in calculus, and so it's very important that you get some practice with this. And in fact, we have, right, because 3.3 and 3.4, those sections really leaded very nicely into curve sketching, which was 3.5. And so we have gotten some good practice, but definitely be prepared. Quite often, curve sketching problems show up as one of these big point problems on the final exam, because, again, it is a very important topic. All right, so let's go ahead and get down to it. Example 5 here, we have a function, and we'd like to find the following, right? So this has very particular things that we want to go ahead and do. And then maybe if we have a bit of extra time here at the end, we can go ahead and put it together and actually sketch it. But this is quite, these curve sketching problems we saw, in the section, they become very long, but we really have to specify what exactly do we want to find with each one of these things. So in this case, I have 4 parts, and then maybe we can put it all together and find a graph. So the first thing is the domain. The domain of the function, this is really kind of something back from our algebra days, but it's certainly come up as we talked about continuity and limits and derivatives and all that sort of stuff. So the domain of a function, right, are all the real values of x that you can plug in, and you get a real value of y or of f out. So the main things that you need to be looking for when you're asking about the domain is that, right, you really shouldn't be dividing by 0. That would be bad. That won't be in the domain of the function. You shouldn't be plugging in negatives into square roots or really any even root, and you shouldn't be plugging in 0 or negatives into natural logs. So luckily we don't really deal with logs so much in this class, but you may, in your Calc 2 class, so it's something important to remember. In this particular function here, we don't have any square roots or any roots whatsoever. So the main thing that we have to be worried about is division, right? You shouldn't divide by 0. And so if x minus 2 was equal to 0, that would be quite bad, right? Then we'd be dividing by 0, and this won't be in the domain of the function. And so we can go ahead and solve here, and it's not so bad, right? Adding 2 to both sides, we see if x is equal to 2, then you'd be dividing by 0, and that's not so great. So the domain of f is everything where x is not equal to 2. So I can even put a little not equal sign there. So if everything except for not equal to 2, well, in interval notation, the answer would look like everything smaller than 2. So those are all the values from negative infinity all the way up to 2, but not including 2. So that's why you use the parentheses here. And then all the stuff bigger than 2. So if you're looking for all the stuff not equal to 2, you have all the stuff less than 2 and all the stuff bigger than 2. And then with math, right, in order to combine two intervals like this, we use a union. So a little u there. And so we have all the stuff less than 2, all the stuff bigger than 2. That's our final answer. So that is the domain. We're going to be able to draw a picture basically everywhere except for at x equals 2. We'll see that there's no point there on our function. All right, part B, critical numbers. Now we're moving into the calculus stuff. So the critical numbers, this is where the derivative is equal to 0 or is undefined. So let's go ahead and take the derivative. So, okay, the derivative. Well, let's see. I have a function divided by another function here, so I'm going to need to use the quotient rule. So let's go ahead and use the quotient rule, and we have the derivative of the top, 16x, times the bottom, x minus 2, subtract away the top, 8x squared, times the derivative of the bottom. I guess that's just going to be 1 here, divided by the bottom squared. So x minus 2 quantity squared. So that's what our derivative is, and we want to know when is this 0 and when is it undefined. Well, okay, again, thinking about when is it undefined, this is going to be wherever we divide by 0 or wherever we plug in a negative into a square root or a fourth root or any even root, or if we plug in 0 or negatives into natural log. So again, kind of the only thing we really have to be worried about for this particular equation seems to be, well, we're dividing by this x minus 2 quantity squared. And so we want to make sure that x minus 2 quantity squared should not be equal to 0. Well, that will give us one of these critical numbers here. And so, okay, well, if I go ahead and take the square root on both sides, oops, I lost my 2 there. So if I take the square root on both sides, and then I add 2 to both sides, we get x is equal to 2. But notice we already took into consideration x is equal to 2 back here in the domain. So there's a kind of a subtle point here that critical numbers need to be in the domain of the function. So actually x is equal to 2 will not be a critical number. And the best way to think about this is that we've already taken it into consideration with the domain. So x equals 2 is kind of out of here. Okay, well that was half of it, right? So you can either have the derivative undefined or equal to 0. So we need to also consider what happens if we had this equal to 0. And so let's go ahead and set this equal to 0. And maybe the first thing that I do here is that I usually say I'm not such a fan of fractions. So again, let me go ahead and multiply through by this LCD, the lowest common denominator, x minus 2 quantity squared. And so that's going to perfectly cancel out here. And of course, whatever I do on the right-hand side, I should also do it on the left-hand side. But in this case, 0 times anything is just 0. So this just becomes 0 over here. So that's not so bad. And on my right-hand side, we have 16x times x minus 2 minus 8x squared. Let's go ahead and simplify a little bit by expanding this out. 16x squared minus 32x minus 8x squared. We can go ahead and combine these like terms here, and we're going to get 8x squared minus 32x. And I think this we can actually factor it, right? So if I factor this and factor out an 8 and an x, in my first term I'll have an x left over, and in my second term I'll have a negative 4 left over. So, okay, and again, we're trying to figure out when is this equal to 0. Well, if you have two things being multiplied together, right, you can get 0 if either the first is equal to 0 or the second is equal to 0. So if either 8x is equal to 0, that means, again, x would be equal to 0 in this case, or if x was equal to 4, right, either one of these cases, you would get 0 overall, right, because 0 times anything will end up being 0. So this gives us two critical numbers at 0 and at 4. And remember, we haven't taken these into consideration yet. The only kind of value that we have taken into consideration so far is 2. And so 0 and 4 are now critical numbers. So x equals 0 and x equals 4 are critical numbers. Now, I've seen some problems, right, have you classify these. And in fact, we have this as our part D down here. So we're going to classify these critical numbers in just a little bit. And we're going to use this fact where it's increasing and decreasing to help us do that. So let's move on to part C here. Where is f increasing and where is it decreasing? Now, this is very important. Increasing and decreasing. And thankfully, you know, in part A and part B, we've actually worked towards this quite a bit. So we've made a lot of headway here. The first thing to do when you're interested in increasing and decreasing is to draw a number line and to split it up at points where either you have breaks in the domain. So for instance, at x equals 2 over here, you have a break in the domain, and so you need to break up your number line there. And then also at critical numbers. So at critical numbers, we found at x equals 0 and at x equals 4. And what we're going to do here is basically we're using the test point method in order to figure out where is the derivative positive and when is the derivative negative, right? Increasing and decreasing is all about where is the derivative positive or where is the derivative negative. So we're very interested in the derivative here. And so I go back, right, and let's maybe simplify down our derivative one more time here. I simplified down the numerator for a while here, and we got 8x times x minus 4. And the denominator, right, when I was actually solving this, right, I got rid of the denominator by multiplying it on both sides. But the actual derivative equation does have this denominator of x minus 2 quantity squared. So this is maybe a nice simplified version of our derivative function. And again, we're going to choose different test values. So I'm going to choose test values in each one of these pieces that I've broken up my interval into. So for instance, I need a number less than 0. So over here somewhere, so I could do -1 or -2 or -5 or -100, right? Whatever your favorite value less than 0 is, that's a fine test point. So I'm going to go ahead and do -1. That seems pretty natural here. Between 0 and 2, well, 1 seems quite nice, especially if I want to plug it in for stuff and I don't get a calculator. If you did get a calculator or a computer, I mean, you could choose a half or a fourth or, you know, 1.359 or whatever, right? So any number between 0 and 2 would work. Likewise, between 2 and 4, since I don't get a calculator, I'm going to go ahead and choose 3. And something bigger than 4, maybe just for fun here, I'm going to choose 10. Right? But I invite you, maybe the more natural choice would be 5. So go ahead and choose 5 and work on that. And then let's see that we actually both get the same result, right? So it doesn't really matter what the test value is that you choose, so long as it's somewhere in that piece of our interval. So, okay, we're going to go ahead and plug these into our derivative function here, and we want to see, is this positive or negative, right? Because positive or negative derivatives tell us about increasing and decreasing. So my first one is -1. I'm going to go ahead and plug that into my derivative here. And so I'm going to get 8 times -1 times -1 minus 4 would be -5, and divided by -1 minus 2, so -3 squared, so that's 9. And so the big thing here, I mean, we could simplify this all down and whatnot, but I see negative times negative, that's going to be positive, and we're dividing by positives and everything. So the big thing here is that this is positive. So on this piece right here, we're going to have the derivative is positive. And again, you could actually simplify this all the way down, but it's not necessary. You just have to know, is it positive or negative, right? What is the sign of the derivative there? Let's go ahead and check at 1. So f prime of 1 there. Again, we're exploring the derivative for increasing, decreasing. So let's see, 8 times 1 is going to be 8. 1 minus 4 is going to be -3. And divided by 1 minus 2, that's going to be -1, but I got to square it. So -1 squared, that's going to be +1. And so altogether, again, we get negative 24, I suppose, here. But the big thing here, again, I see positive times negative. That's going to be a negative numerator divided by a positive denominator. So a negative divided by a positive is certainly going to be negative. So the big thing here is that we have negative. Okay, well, what about at 3? So f prime at 3. And so if I go ahead and plug in 3 everywhere, well, we see 8 times 3, that would be 24. Times 3 minus 4, that's going to be negative 1. And divided by 3 minus 2, that's going to be 1 squared, that's 1. And so again, 24 times a negative divided by a positive, that is going to be negative altogether, right? There's one negative sign there, and so it doesn't cancel out with anything, and so this is going to be negative. And then finally, I chose 10, right, as a bit of a silly one, and I invited you to go ahead and choose something a little bit more natural, like 5 or maybe 6 if you prefer. But I went ahead and chose 10. And so if I plug that into my derivative equation, again, thinking back here, 8 times 10, that's going to be 80. Times 10 minus 4, that's going to be 6. And divided by 10 minus 2, that's going to be 8 squared. So it's going to be 64. And I see a positive on top, positive on bottom. Positive divided by positive is going to be positive. So, right, this is greater than 0. And so we have a positive derivative bigger than 4 there. And again, you would get that same positive result if you chose 5 or if you chose 6 or if you chose any value there, right? You would get, again, kind of all of these test points work to classify the piece of the interval here. So, all right, now we're all set to go ahead and write down our final answer. We know that f is increasing on the interval from negative infinity all the way up to 0. So kind of on this piece right here where the derivative is positive all the way up to 0, that it's increasing. And again, that's because the derivative there is positive. And likewise, the derivative is positive again after 4. So, and again, bigger than 4. So 4 and bigger, that would be 4 to infinity, and we use parentheses, right, because you're not including those. And then f is decreasing. And let's see, everywhere where it's negative, the derivative is negative, would give us a decreasing function. So I guess from 0 to 2, so 0 to 2, and then again after 2 until 4. So 2 until 4. And again, we have a little union to say, well, it's kind of in both of these places, right? We have that the function is decreasing. All right, and so there is my final answer for part C. Let's go ahead and do our final part, part D. We want to go ahead and classify our critical numbers as either local mins or local maxes, right? So we want to find any local maxima or local minima of f. So the first thing, local maxima and minima are always critical numbers. So we need to be looking at our critical numbers here, 0 and 4. And in fact, I like to do this, and it follows quite quickly from part C. So I'm going to go ahead and just draw in a little picture of our function here. Maybe I'll go ahead and use, I'll jump over here to my draw tab and get a different color. I don't want to use red because it's not wrong by any means. I guess I'm going to use purple. So, okay, I'm going to draw a little picture of what's happening with f. Again, so if we have a positive derivative, we know that f is increasing. And then after 0 here, we know that our derivative is negative, so we have decreasing. So it's going to look something like this, increasing and then decreasing. So at 0 right here, you can see I've even drawn a little picture that 0 is going to be a local max. Now, 2 isn't a critical number, so we don't have to actually worry about this. But if you were to look at it, it turns out, right, at 2, we have our derivative is negative, so we have decreasing. And then after 2, our derivative is still negative, so it's decreasing even more. Right, and so therefore, right, this is going to be neither a local min nor a local max. Again, it's not really even a critical number, so we don't have to worry about this. Okay, but around 4, right, that's our other critical number that we have to be worried about. So the derivative is negative, that means that we're decreasing. And then after 4, the derivative is positive, so therefore we're increasing. So if you kind of look at the picture here, this looks like a minimum, right? Something down here would be a minimum at 4. So this would be a local min. So we don't need a whole lot of work here in order to show this. just kind of going back to our number line, this gives it to us fairly quickly. So the result here is that x equals 0 is a local max, and x equals 4 is a local min. All right, and from that, right, we've answered all of the questions, but I think we have a little bit more time. Let me show you how to kind of combine these things into a graph. I also want to notice maybe before we go about that, right, that this only used the first derivative stuff. Definitely we can see longer problems or other problems where it asks about inflection points and where is it concave up and concave down and all that sort of stuff. In the interest of time, right, I excluded those. I already know that we're close to an hour or so for our video. But you should be prepared, you know, and you've seen these in web work, homework, and whatnot as well. You should be prepared to do both first derivative, increasing, decreasing sort of stuff, local mins, maxes, and also the second derivative, inflection points, concave up, concave down. It's a very similar storyline, right? Again, you just draw out a number line, but now you're very interested in the second derivative. So you get a lot of the same sort of stuff. All right, so but let's go ahead and combine all of this information into the best graph we can with this information. So I'm going to go ahead and draw a picture of a graph here. And what I like to do is I like to break it up along all of our points of interest. So I'm going to go ahead and maybe use, I need maybe a way to keep this purple pen around. So I'm going to use purple here, and I'm just going to break it up, right? And kind of all of our points of interest are at, let's see, x equals 0, x equals 2, and x equals 4, right? So these are all of our points of interest. In fact, we saw them on our number line as well, 0, 2, and 4. And so I'm going to go ahead and break up my two-dimensional picture along these values. So x equals 0, that's right here. So this is along the y-axis. So x equals 0. If I move over here to maybe x equals 2, again, there's going to be something different happening here. So along x equals 2, that's going to be something where, you know, we get changes. And then along x equals 4. So x equals 4 right here. So I just do a little dotted line here to showcase that something's changing here, right? And now I'm going to go back and try to collect my information that we have from all of these parts. So, right, for instance, the domain. The domain of f, that was where the x equals 2 first came up. We were dividing by 0 at that point. And so we remember probably from our 1.5 stuff, and again in 1.8, that we're going to have a vertical asymptote there. So at x equals 2, we have a vertical asymptote. And so I'm actually going to switch this, and instead of a purple dashed line, I'm going to go ahead and use red here to showcase, right, that we have a vertical asymptote at x equals 2. So vertical asymptote, that's just how I'm going to remember that. So I definitely don't want to draw a dot or anything on there, right? You're not allowed to touch the vertical asymptote. Okay, next up, when we were doing maybe like part B and whatnot, we found out that 0 and 4 are critical numbers, right? And later on, we classified those as you're going to have a local max and a local min. So maybe at x equals 0, I'm just going to put, just to remind myself, that I'm going to have a local max here, if all goes well. And at x equals 4, I'm going to have a local min. This just helps me look at my picture at the very end and verify that I haven't made a mistake. All right, lastly, we have information about where is the function increasing and decreasing. So, okay, we have increasing everywhere smaller than 0. So everywhere smaller than 0. So over here, we're going to have an increasing function. And then from 0 to 2, we have decreasing. From 2 to 4, we also have decreasing. And then after 4 and kind of forevermore, we have increasing. Okay. All right. Lastly, usually I like to find like one point to kind of pin this all to, at least. Sometimes you see kind of these problems where it explicitly says find the, vertical intercept or horizontal intercept. In this case, it doesn't say that. But I'm going to go ahead and just plug in 0 and 4. Right, just because these are kind of points of interest, they're going to be our mins and maxes, and that'll give us a couple points to actually pin this to. So remember, I can't plug in 2, otherwise I would, but that one you're dividing by 0, and so that doesn't work out so well. So if I plugged in 0 here, we'd have 0 divided by -2, and that gives me 0. So when I plug in 0, I get out 0. So that tells me that this point right here, 0, 0, is a point on our graph. Again, this just gives me something to kind of pin my function to nicely. Let's also plug in 4 because that's another point of interest. So f of 4, so when I plug in 4, let's see, I get 8 times, let's see, 4 squared would be 16. Divided by 4 minus 2, that's going to be, well, 2. 4 minus 2, 2. Okay, so let's see, if I go ahead and divide 16 divided by 2, that's going to be 8. So 8 times 8 is going to be 64. Wow, that's really far up there. Okay, so at 4, I get 64. So at 4, I'm just going to go ahead and put up here that this right here is 64. So if I plug in 4, I get out 64. All right, so there we go. Now let's go ahead and try to connect all of these dots together. Remember, kind of to the left of this one, I need to have an increasing function. So maybe I'll have increasing, and it needs to go and it needs to hit this point here. So maybe something like this. After this, right, we have decreasing, right? So decreasing, it needs to be going down. And remember, we have this asymptote here. So let's get closer and closer to this asymptote, and we're not going to be touching it, but okay, it goes maybe something like this. Okay, now after 2, we need to decrease again, right? So kind of as you jump over this asymptote, there's a question about, okay, should I start up here or should I start down here? And because we have decreasing, right, this one wouldn't really work out. This would be increasing. So therefore, it needs to kind of jump up here, and there we're going to have decreasing. Now, don't forget, it's got to be decreasing the entire time, and I need to hit this point. So I've probably gone too far. I would need to kind of wrap around, but then here it'd be increasing. So that's not so good. So I need to make sure to draw this maybe a bit more shallow or something like this. I need to be decreasing, but I need to make sure that I hit this point. So something like this. So now it's decreasing the entire time, but I actually hit that point. And then after x equals 4, it's increasing. So something like this. Now, I gave all of these pieces kind of curvature, right? And we didn't discover, you know, if these were concave up or concave down or what exactly was happening. If you had a more thorough problem where it had, you know, parts E, F, and G or something like this, right? Maybe you know something about your concavity, and then you could include that in your picture as well, right? Should it be curving up? Should it be curving down, right? What is the concavity telling us about these things? But as of right now, this is kind of the best picture that I can come up with for my first derivative information. All right, and with that, we are done with example number 5 and the recap video for this, the recap problems for this video. I hope you guys enjoyed. Good luck on your quiz tonight. And again, we have only a couple weeks until our final exam, so it's never too early to start studying. All right, I'll see you out there.